Well done for making it to the final module. You should now be familiar with the three load types: resistors, capacitors and inductors. In this section we will look at the effect these different loads have on the electrical power. The aims of the course are to show the basic power equation, to look at the relationship between the power of a device and its current, to introduce the theories of real, reactive and apparent power. The electrical power is the amount of energy that is drawn from the system. The main equation for electrical power is as follows. The power P, measured in watts, equals the voltage V, measured in volts, multiplied by the current I, measured in amps, multiplied by cos phi, which is the power factor. Phi is the angular difference between the voltage and current waveforms. In most electrical systems the voltage is constant, so the power is directly related to the current. As the current increases, so does the power drawn from the system. Let's do a worked example. For a circuit which draws 1400 watts from the source, has a voltage of 240 volts and a power factor of 0.8, calculate the current drawn from the system. P equals V times I times by the power factor. Therefore, transposing the equation, I equals P divided by V times by the power factor. Therefore, I equals 1400 watts divided by 240 times 0.8 from above. Therefore, I equals 7.29 amps. As we stated previously, as the power of a device increases, so does its current, as the voltage is fixed. Let's look at some typical 240-volt household devices. Firstly, we have a 60-watt bulb. Assuming a power factor of 0.8, that will give you 0.3 amps. Next, a 150-watt television. That will draw about 0.78 amps. Next, a 1000-watt kettle. That will draw 5.2 amps. A 1500-watt iron. That'll draw 7.8 amps. A 2000-watt washing machine, 10.4 amps. And finally, probably the biggest load in the home, a 3000-watt cooker. That'll draw 15.6 amps. Let's now remind ourselves about the phasor diagrams for the three main loads. First we have the resistor. In a resistive circuit, the current and voltage waveforms are in phase. There's no phase angle between them. The power factor is 1. Next we have an inductor. In a purely inductive circuit, the current lags the voltage by 90 degrees. The power factor is 0. And finally, a capacitive circuit. In a purely capacitive circuit, the current leads the voltage waveform by 90 degrees. The power factor is 0. Let's now remind ourselves of the impedance triangle for an inductor-resistor combination. For this combination, the resistance vector is horizontal. The inductive reactance vector is 90 degrees behind. The impedance vector Z is the summation of the two. The phase angle phi is the difference between the resistance vectors and impedance vectors. The power triangle is very similar. First we have the real power vector P. Let's make that horizontal as a reference point. 90 degrees behind that is the reactive power vector QL. Finally, the apparent power vector S is the summation of the real power and reactive power vectors. Phi is the phase angle difference between the real power vector and the apparent power vector. Let's now look at the impedance triangle for a capacitor-resistor combination. First we have the resistance vector R. Let's make that horizontal as a reference point. 90 degrees in front of that is the capacitive reactance vector XC. The impedance vector Z is the summation of the two vectors. The phase angle phi is the difference between the resistance vector and the impedance vector. The power triangle is very similar. Firstly, we have the real power vector P. Let's make that horizontal as a reference point. 90 degrees in front of that is the reactive power vector QC. The summation of the real power and reactive power vectors is the apparent power S. Phi is the phase angle between the real power and the apparent power vectors. Let's now look at the different types of power. Firstly, the real power P, which occurs when we have resistors in a circuit. The real power is measured in watts. Next we have the reactive power Q, which occurs when we have inductors or capacitors in a circuit. The reactive power is measured in vars. Next we have the apparent power S, which is the summation of the real and reactive powers. The apparent power is measured in VAs. The power factor cos phi represents the difference between the real power and apparent power vectors. Let's look at some of the common power equations we use. The apparent power S equals the voltage V times by the current I. There is no power factor required for the apparent power. Using basic trigonometry, the real power P equals the apparent power S times by cos phi, the power factor. Therefore, the real power P equals the voltage V times by the current I times by the power factor. These power equations can be applied to both single-phase and three-phase AC systems. Let's do a worked example. For a single-phase AC system where the voltage is 240 volts, the current is 150 amps and the power factor is 0.8, calculate the real and apparent power. The apparent power S is the voltage times by the current. Therefore, from above, the apparent power S equals 240 volts times by 150 amps equals 36,000 VA, or 36 kVA. Real power P is the apparent power times by the power factor. Therefore, the real power P is 36,000 VA times by 0.8, therefore equals 28,800 watts, or 28.8 kilowatts. Let's now summarise what we've learned today. As the voltage is normally fixed, as the power of a device increases, so does its current. The power is dependent on the voltage, current, and power factor. There are three types of power: real power P, reactive power Q, and apparent power S. Congratulations for completing the course. I hope you found it rewarding and interesting. As usual, I've attached some test questions on the course content. The next module in this course will show you how to use all of the basic principles you've learned on this first module to design an electrical power network. I hope to see you then.